I'd like to thank everyone who invited me here today and all of you who came here today to be part of this amazing event. I'm really glad to be here. So I wanted to tell you a little bit about self-driving. So I work at Uber ATG. That's the branch of Uber that is developing a self-driving vehicle. And autonomy is how we call the core technology, the core algorithms for self-driving. So what we do is we use AI, right? And a lot of people talk about AI these days, and even as far as 1956, John McCarthy, who was one of the grandfathers of AI, said that as soon as it works, no one calls it AI anymore. But AI is effectively the attempt, it's a discipline within typically computer science that deals with trying to automate intelligent behavior. And as such, it doesn't really give any prescribed way of how to do it. Within AI, there is the branch of machine learning, which says, well, if you want to generate intelligent behavior, you do it by learning from data. And deep learning, which is a term you might have heard thrown around, is a particular way of doing it. It's inspired by how the brain works with neurons that communicate with each other. As a piece of technology, it's quite far from how the brain actually works, but it was definitely the inspiration. Thank you. So at Uber ATG, we're working on, here in Toronto, we have an R&D center. So it's a scientific research center, meaning that we have a large group of researchers who are doing active research, publishing papers, sharing the knowledge of how we're advancing the technology with the world. And then we also have an engineering and research engineering arm, which I lead, where we take these core algorithms and help put them on the car. So, so that's the part I get excited about. How do we bridge this gap between research and applications, research and product? So self-driving as a discipline is very exciting because, you know, we all, well, I don't know if we all want to sit in a self-driving car, but I definitely want to. Because it's time we spend, that we can be spending doing other things, being more productive than just driving. And I think it will eventually lead to a safer world because cars, you know, they don't get tired, they don't drink, they don't text, right? And we will be able to do all of these things. And once upon a time, we used to train a horse to take us somewhere, whereas now we're trying to train a car to take us somewhere. So, you know, it's a fun game that we're playing. But it's also important, right? Because I believe that we will eventually have less casualties in the roads. I believe that it's more than that, that we will be able to open up our public spaces a bit more or quite a lot more, because right now, if you look outside, there's all these cars that are parked along the roads, and the average car spends about 95% of its time being parked, okay? Think about that. So we have all these huge hunks of metal sitting around doing mostly nothing most of the time. With the combination of self-driving, of ride-sharing, which is the direction that Uber is focusing on, and electric cars, we're going to have a safer, cleaner technology that allows us to have a lot less congestion and pollution in the roads. However, it's also very complex. So how does it work? We have a car. This is one of the Uber self-driving vehicles. And we basically have a whole bunch of eyes and ears, as it were. So we have sensor technology that has to do with cameras that are mounted on top of the car, a technology called LiDAR, which is this swinging array of laser nodes and so laser emitting mechanism. And we have radar, sonar, and so on. So this is how we sense the world. And then at the end of the day, we need to provide two things. We need to do the acceleration, and we need to do the steering, right? These are the 2 degrees of freedom we have basically with driving the car. So the question of self-driving is how do we go from all of this input information, and what I'm showing here is you have some camera input as well as a particular way of looking at how the LiDAR data appears. So this is kind of looking from the top down. That's the blue thing on the side. And we need to go from sensors to controls. The way we think about it is we have our sensors, and the first thing we need to do is perception. We need to understand where is everyone that we care about in this scene, in the 3-dimensional world? Where are they localized? Is it a person? Is it a car? Is it a cyclist? Is it a motorcyclist? So perception is the task of understanding who are all the actors, as we call them, in the scene that we're in right now. Once we know where they are, we want to do prediction. We want to estimate where they are going to be in the next 100 milliseconds, 1 second, 5 seconds. We need to know where they're going and what we think they're going to be doing. Once we have that, once we know where are the actors and where they're going to be, we have to motion plan. We have to understand how to take the car itself from one place to the other where we want to go without colliding with anything, and doing it in a way that respects all the laws of the road, and doing it in a way that is actually comfortable for the human rider, because you also don't want to brake and steer too hard. So that's the motion planning. And once we have the motion plan, we can set it out for controls. Underneath all of the technology, we also have to know at any given point in time exactly where we are on the road, and this is called localization. Localization is, I know that I'm in this particular point. In this particular point where? On a map, which is this high definition map. It's a very special type of map. It's not your Google map. It knows everything about where the lanes are and all the stop signs and all the traffic lights, and which lane can turn where. So at any given point in time, we know to the degree of a couple of centimeters where we are on this map. And so what I'll do in my last remaining minute is show you two pieces of technology that were developed here just across the street at the Uber ATG office. The first one is a particular algorithm for detecting where the different actors are. So this is part of the perception aspect that I talked about. And what's special about this algorithm is that it takes into account both the LiDAR information as well as the camera information. And the neural network learns how to merge these two things in a way that makes use of all of these different types of data. So the nice thing about cameras is that you can see in quite a bit of detail very far, whereas LiDAR is sparse. You don't know what's happening very far from you. But on the other hand, cameras don't tell you where in three-dimensional space the information is, because it's already a projection, whereas LiDAR does tell you that this thing is about 20 meters away or 100 meters away. And then the second piece of technology that I will briefly show you is called segmentation. So in segmentation, instead of drawing these little boxes around where the cars are and the people are, which is the typical task of detection, as we call it, in segmentation, we're trying to account for every single pixel in the image. So on top, you see the input that goes into this neural network algorithm. And on the bottom, you see how every pixel in the image has a color associated with it, the color being whether it's a car, a tree, the road, and so on. So this is the task of segmentation. Both of these algorithms have been published and are beating the state of the art in academic benchmarks. And both of these algorithms are well ahead on their way to being integrated into our self-driving car technology. And that's it for me. Thank you very much for listening.